Greetings, everyone. I'm actually on vacation in the countryside, so I've decided to record my presentation just to be on the safe side with respect to internet connection. So first, I'd like to thank the organizers of this session, Diego, Luis, Jan Felipe. Thank you very much for putting this together and also kindly inviting me to make a presentation. So we'll talk about the Askey polynomials on the unit circle and offer an algebraic interpretation through what we have called the meta-Jacobi algebra. So let's get going. Sorry, this has been on standstill for too long. So in his edition of the collected works of Sigel, Askey introduced these polynomials on the unit circle, which will be denoted by P sub n. They're given by a 2f1 series, where you notice that the degree arises in the numerator and the denominator parameters. These polynomials are biorthogonal. Their partners, the biorthogonal partners, are expressed in terms of these polynomial q sub n, which are obtained just by interchanging the indices alpha and beta. They are normalized so as to be monic. And the orthogonality of these two families is expressed here. So you see that if you integrate on the unit circle, P times Q, but of the variable 1 over Z, with something like a Jacobi weight, well, you have orthogonality. The branch of the multi-valued function needs to be defined appropriately, and this is explained here. Having introduced these polynomials, Askey voiced the opinion that these are natural analogs on the unit circle of the Jacobi polynomial that we know quite well. And let me just, to keep that in mind, give you a reminder of what these Jacobi polynomials are. We take them to be on the interval 0, 1. They are, of course, given in terms of, again, the 2, 5, 1 series. But notice that in this case, the degree arises twice in the numerator parameters. And the orthogonality relation is the usual one with the weight that we know well. These polynomials, the Jacobi polynomials, they obey a differential equation, very well known, involving the hypergeometric operator. So this operator acting on the polynomial produces this quadratic eigenvalue. Now, the bispectral properties of these polynomials are encoded in an algebra that we call the Jacobi algebra, J, generated by 3 operators, K1, K2, K3, and these could be defined by taking K1 to be minus m, the hypergeometric operator, K2 being multiplication by x. And if you take the commutator, you see that this provides you with relations that close quadratically on the generators. And it is well known that from the representation theory of this algebra, one can recover all the characterization of the Jacobi polynomials. Now, recently, looking at polynomials and rational functions of the Hahn type, we saw a scheme arise that gives indication that we could be moving towards an algebraic descriptions of bispectral biorthogonal functions. Let me summarize what we observed in this study, as it will be relevant to what I'll be talking about in the course of the talk. First, it is known that if you consider generalized eigenvalue problem, and this will be prominent in the course of the talk. That is, eigenvalue problems where you have two operators appearing in the following fashion. M acting on the eigenvector is equal to the eigenvalue times L, another operator acting on the eigenvectors. What is known is that such generalized eigenvalue problem lead to biorthogonal rational or polynomial functions when these two operators that define the problem, M and L, act tridiagonally. So when one look in the special case that we've analyzed at Hahn type function, to these two operators, M and L, it's possible to add a third, X, which has the following features. The biorthogonal functions that we are describing are seen to arise as overlaps between various bases. On the one hand, the GVP basis, which I'll call Dn, and the standard eigenvalue basis, E star, which will be the eigenbasis of the adjoint operator, the adjoint of X, the third operator that we have added to M and L. And then in this framework, the biorthogonal partners are given as overlap between the bases Dn star and E and Z of the adjoint problem. Okay? So this, interestingly, offers a picture which is parallel to the description of hypergeometric polynomials with Leonard pairs. The differential or difference equation of these biorthogonal functions follow from the this operator m minus lambda n times L, which on the one hand annihilates the n, the eigenbasis of the generalized eigenvalue problem, and the fact that this operator also acts tridiagonally on the basis E star of Z, the eigenbasis of X transpose. The recurrence relation that completes the bispectral picture is obtained as follows by forming out of the, in fact, the adjoint of X and L, this product, L transpose X transpose, to get an operator R transpose. And again, we have some dual properties for this operator. This operator will annihilate EZ because you see from the presence of X in the construction of R, and given that this EZ is star is an eigenvector of X transpose with eigenvalue Z, you see immediately that this will give 0. And it is also observed that this operator conversely will act tridiagonally in the basis Dn. And this is the picture that provides the bispectral relations that we care to describe. This can then be put in algebraic terms. The rational Hahn algebra, which is generated by these three operators that we've brought in, this algebra called rational will account for the two generalized eigenvalue problem, the initial one involving M and L, and the second one built in terms of R, involving R and L. And these generalized eigenvalue problems are at the root of the bispectral relations, as I've indicated. Now, since R is made out of the products of X and L, it means that the rational Hahn algebra is in fact embedded in a meta-Hahn algebra, this one, MH, being generated by M, L, and X. And then there's a simultaneous picture for the polynomials themselves, the Hahn polynomials. In this case, these polynomials are, as is rather known, the overlaps between the eigenvalue basis of X transpose and the eigenvalue basis of the linear pencil made out of M and out of L. Call it W, and it involves a parameter mu. And you have the same Hahn polynomials would arise in the overlap between the dual problems. So the bispectrality of the orthogonal polynomials is explained by the Hahn algebra, which is generated by X and W. And so we see in the end, in the Hahn case, that the meta-algebra, I recall generated by L, M, and X, this algebra, this meta-algebra, subsumes both the rational by Hahn algebra, which explains the biorthogonal rational functions, and the Hahn algebra, which explains the properties or the bispectrality of the Hahn polynomials. So that is in ways of background. And having observed that, we believe that this approach, which gives a unified description of the biorthogonal and orthogonal functions of Hahn type, that it extends beyond these the special classes of family. And the purpose of the talk here is to add support to these views by providing a unified treatment of the Askey biorthogonal polynomial on the unit circle and of the Jacobi polynomial. And in the course of this analysis or study, we'll obtain the bispectrality of the Askey polynomial as a byproduct. So in broad stroke, the talk will go as follows. I will first introduce the this meta-Jacobi algebra for the case that we are looking at. And then we'll see how the special functions arises as overlaps between generalized eigenvalue problem and ordinary eigenvalue problem basis on a module of the meta-Jacobi algebra. So we'll look at representation of this algebra, and on the representation space, we'll look at various eigenvalue problem and that overlaps between the bases associated to these problems. The orthogonality or biorthogonality properties of the families that will arise through these overlaps will then follow from the framework. And in the last part, we'll construct a differential model for the algebra, and out of it, we'll obtain the bispectral equations and contiguity relation for the Askey polynomials. All right, that's our plan, so let us get going. First, we'll introduce this meta-algebra. So it's a unital algebra. It will be denoted MJ. It is generated by, again, three operators. We use the same letter, L, M, and X. And these generators obey the relations that are here. Again, you see that they are quadratic in nature. Commutator of L and M is quadratic in L. L with X is linear, and M with X, again, involves something bilinear in X and L. The parameters alpha and beta will be the parameters that will arise in our special functions. So this is the meta-Jacobi algebra. It has an invariant, a Casimir element, which is cubic, as you can see here. And what I will mention now is that this algebra is in fact isomorphic to the universal algebra of the Lie algebra SU11 taken to be defined on the reals. This algebra is most likely very familiar to all of you. It has three generators, J plus minus and J naught. It satisfies these commutation relations with this Casimir. And the isomorphism between MJ and the universal of SU11 is established by noticing that if I take L, M, and X to be given by these expressions in terms of the generators of SU11, notice that here you have a quadratic expression for M. You observe that given the commutation relations of the SU11 generators, that L, M, and X verify the commutation, the defining relations of the meta-Jacobi algebra. And it's isomorphic because you can readily see that this map is invertible. The hence a relation between the Casimir J square of SU11 and the Casimir Q of the meta-Jacobi algebra, and that relation is given by the expression you see here. Now, Jacobi algebra, one fact to notice is that explains the bispectral property of the Jacobi polynomial, obviously as an embedding in the meta-Jacobi algebra, because you recall that having K1 given by minus M and K2 by X, we were realizing the Jacobi algebra, which I reproduced here to help your memory. But then M and X are generators of the meta-Jacobi algebra. So the upshot is that this provides for K3 an explicit expression. It resolves K3 in terms of X and L, and therefore obviously provides the embedding of J into MJ. Notice that in this case, the parameters are given, some I've made explicit, and there's this D here, which is expressed in terms of Q, the Casimir of meta-Jacobi, of the meta-Jacobi algebra. So in fact, we have an embedding of the Jacobi algebra into it's rather the universal Jacobi algebra that gets embedded into the meta-Jacobi algebra. Okay, now in the following, we will use irreducible representation of U11, the universal, identified as the meta-Jacobi algebra, to work to construct representation of the presentation that we have of this algebra. Now, in SU11, or the irreducible representation of SU11, are such that the Casimir here are given by this expression where tau is some real number. So we shall take this tau to be given by this expression in terms of our parameters, alpha and beta, that will all along be there and arise in the polynomial. And you notice that because of the relation between Q and J square, that this will give for Q this expression, which is all consistent because you recall that our parameter D involved the Casimir of the meta-Jacobi algebra, but with this choice for the parameters, we recover what is the right, or what is the expression for D that will be connected to the standard Jacobi polynomial. Very good. So we now have our algebra. This is the algebra upon which all the analysis will be based. And now we move to discuss representations and how special functions will arise as overlaps between bases for representation. So as I've indicated, we will infer the representation of the meta-Jacobi algebra from one representation of the universal algebra of SU11. We shall consider a module with basis tau k, with k running over all the natural, all the integers, pardon me. And so the actions will be like this. J0, I recall, I'm providing now a representation of SU11. J0 will act diagonally in this basis. J plus will be a simple raising operator, and J minus will be lowering. It should be said that this representation is not unitarizable. It can be readily seen. There's no way, because you see, when k is equal to 0, this will vanish, and so you cannot go down beyond 0 if you hit 0. But if you were at -1, you could keep going down. And while for plus, you will run over all the integers. So there's no way you can turn J minus into the adjoint of J plus. These actions are not compatible. It is also reducible because I've already indicated that the positive discrete series is a submodule of this module. This arises when k is only over the positive integers. Okay, but this is the representation that we want to take. I'll justify later why we need to use such non-unitarizable and reducible representation. The isomorphism between the USU11 and the meta-Jacobi algebra immediately yields a representation of the meta-Jacobi algebra, and using the expression of L, M, and X in terms of the generators of SU11, you readily see that you have these actions on this module. Okay, L is diagonal, M is two diagonal and lowering, and X is raising and two diagonal. The adjoint actions are directly read off from these actions. As I really already indicated, key will be overlaps between various bases on this module for the meta-Jacobi algebra. And I will just immediately give you an outlook of which basis we shall be using. We will bring generalized eigenvalue bases, Pn and Qn, which are associated to the action of M and L and their transpose. This defines the first set of bases. It is quite immediate to see that these two bases satisfy the following orthogonality relation. I'll come back to that. When M is different than N, we have this relation. Another set of bases are the eigenbases of X. I'll denote them by Z, these bases, and their transpose with Z tilde. The eigenvalue is Z. And the third set of bases will be the eigenbases of M, and so those I will call J, will be connected to the Jacobi polynomials, and of course the tilde associated to the transpose. So we'll now look at these bases in more detail. Let's first start with the eigenvectors of X and X transpose. I remind you that X has this simple action, combination k plus 1 and k, and the transpose obviously k minus 1. It's easy to check that, you know, this is just basically translation, that the eigenvectors of X will be given by this combination of the basis that we've introduced to define the module with these coefficients. Okay, it's almost immediate to see, but you understand that to find an eigenvector of shifts by 1 or minus 1, that you need to define your basis over the full set of integers. And this is the reason for as to why an infinite dimensional module is required. Okay, so these will play an important role. So they are these combination of our vectors tau k with these coefficients involving z, with z being the eigenvalue. Readily, one can check that these eigenbases, z and z tilde, they form orthogonal and complete sets. This provided that the two constants here, which were a priori undetermined by the eigenvalue problem, if you need to establish a relation between the two, namely that A is A tilde plus 1. Provided you have that, you check that you have this relation, namely that z tilde prime scalar z is given by the delta function. This arises from the Fourier representation of the delta function. This is what we are dealing with. And then you also have, provided you have the same relation, the completeness relation, where C, the contour is the unit circle, which is infinitesimally deformed so that the singular point z equal 1 is inside the contour. And in that case, you have this completeness relation. These two relations will play an important role. Okay, so that's our first set of eigenbases, the basis z. Now I come to the generalized eigenvalue basis, P and Q. Okay, so they come from these, well, I forgot to put the bras. I might as well do it now. So these bases are defined by these two generalized eigenvalue problems. So recall, we know the actions of M and L. So from looking at the determinant of this operator, M minus nu L, it's easily seen that the eigenvalue are just given by the integers. Now, in principle, we should do the analysis for both n positive, negative integers, but the results are dual. And in fact, we can limit ourselves to n non-negative. For details of the other case, you can just go check our paper. So we'll do that. We'll take n non-negative, and then we'll just expand or try to expand this eigenvector that obeys this relation in terms of the tau k basis with these coefficients d and k. Enforcing the generalized eigenvalue equation yields a two-term recurrence relation, which I've written down here. And then it's easy to see that all these coefficients d and k will be 0 if k is bigger than n. Well, you see that we're already k is equal to n. This term will be 0, and so you cannot reach k plus 1, hence, and it iterates. So, having observed that, you pursue and you find that the solution is given by this expression, which obviously has the character of hypergeometric expansion coefficients. Okay, so this provides our solutions to the generalized eigenvalue problem for P. And similarly, if we look at the adjoint problem, I remind you that for Qn will be solution of the adjoint the M adjoint acting on Q gives nu N times L adjoint on Q. You proceed similarly. You find that the coefficients D star are 0 if K, in this case, is smaller than N. And so you just to parameterize things, you just set L, the argument to be M plus L, with L starting at 0 and up. And those are the expression for these coefficients. Very well. So this gives us another set of bases. And from simple linear algebra, it's easy to see that PM and L transpose QM are orthogonal. It goes like this, right? So you start with this, with M acting on the left on P. Well, because of the generalized eigenvalue problem, N on P is N times L. Then this is also equal, use the pointer, to M transpose on Q. M transpose is M times L transpose. And so I can bring again the L back. So this is equal to M times PL. And then you just compare the two. You subtract the two, and you see that this, of course, that this must be 0 if N is not equal to M. So this explains the orthogonality. And now you can check that explicitly from the expressions that we have obtained to find precisely the following relations, that this vector and this vector are orthogonal, and moreover, the norm can be obtained and is given here. Good. Now let's see how all this leads to the Askey polynomials and their biorthogonal partner. We'll use the completeness and the orthogonality of the bases that we've introduced to show, this is the result, that the projection of the vector Pn on the eigenvector of X transpose, and similarly, this projection of Z over the eigenvectors of X of these vectors, L transpose Q, these will be the two families of biorthogonal functions on the unit circle. Okay? This is easy to see, and in fact, they'll turn out to be related to the Askey polynomials. But let's first focus on the fact that these are two biorthogonal families on the unit circle. Well, you just form the scalar product of these two functions of Z by integrating over the unit circle. Now recall the completeness relation. So this integral just has the effect of making Z star Z go away through the completeness. So you arrive here, and we just saw that this satisfies this relation. So here, there is your orthogonality relation. Let's now look at the explicit expression. Well, we know everything now. So to compute this scalar product, well, we know what Z is in terms of the vectors tau k, right? You recall we had this coefficient. And for P, it was given by these coefficients also of the vector tau L. We are taking the scalar product, so these basis vectors were taken to be orthonormalized. We get a Kronecker delta, we lose a sum, and taking into account the explicit expressions for the parameters, we know that the sums will reduce to a sum from 0 to n, and these add hypergeometric character, so we build, taking some constant factor or non-n dependent or non-sum dependent factors out, we get this 2f1 expression in the as an expression of the scalar product. Notice that all along, because of the expression for the eigenvectors of x, 1 minus z is the variable. And now you use the FAP formula, which expressed the 2f1 of 1 minus z with a negative integer as a 2f1 of z, and you see that this overlaps, as promised, is basically the Askey polynomial. Because in the process here, converting here to here, you'll bring the degree both to the numerator and the denominator. That is a key result, which I had announced, that the overlaps of between a generalized eigenvalue vector and an eigenvector of the operator x was the Askey polynomials. Okay, similarly, you work in the same fashion, and if you compute this overlap involving Q and the operator L transpose, you naturally arrive at this 2f1 involving 1 over 1 minus z. Notice that in this case, you will have this factor also, z minus 1 to the minus m minus a. And now, if you use the fact that any three solutions of the apogeometric equations are linearly related and you combine them with homographic transformation, you can make the biorthogonal partners appear. You can rewrite this expression we have here into the following form, where you see you have two terms. Let me first tell you that the biorthogonal partner occur in the second term. Here they are. And you have the transcendental factor in front of these polynomials in Z. But you have another term, which could be a bit surprising, but this is just, you see no factors of Z here. So this is just a power series. So we have again seen how the biorthogonal partners, the polynomial, how they appear as overlaps over the module, the MJ module that we have been using. Well, the biorthogonality, as you expect, will then naturally follow. We had observed that these two functions of Z were biorthogonal. And now we know that these are related to the Askey polynomials and their partners. So you do that in detail, but when you multiply, you see that there's a factor in Z minus 1 to a certain power. The two parts in each of the matrix elements contribute to give 1, conspire to give 1. So this is no problem. You may worry about the presence of this term, but that for the other piece here, you see, I told you that these factors conspire to disappear. This was the A tilde and there's something analogous in the other expression. So then you multiply a polynomial with a power series and you will integrate over the unit circle. There's no residues, so this will contribute 0. So in the end, you're only left with the multiplication of the polynomial with this other partner, polynomial partner, with the transcendental term, which is there. And lo and behold, when you just put everything together and take care of the factors, you obtain this orthogonality relation, which turns out, of course, to be exactly the one that Askey had found by different methods. So this gives you an algebraic derivation of the orthogonality or biorthogonality of the Askey. Now I want to show that you can obtain the Jacobi polynomials in a similar fashion. I'll go faster because time is running. But we know that X and M, that they generate the Jacobi algebra, which is embedded in the meta-Jacobi algebra. So we therefore expect the Jacobi polynomial as overlaps between the eigenvectors of X and M transpose or vice versa. And it's the same idea. So you compute the eigenbases of M and M transpose. We know the action of M on the basis elements tau k. From this action, we readily see from the diagonal term that the eigenvalues of quadratic of that form. So you set up, you expand this eigenvector of M in this fashion, you set up the eigenvalue problem, and you work out what the eigenvalue equation entails. It will again give a two-term generating function, which you can solve, and you see these expansion coefficients are given by this expression. And you work similarly the eigenvectors J tilde of the adjoint problem, same story, and you check, as should be, that J tilde and J will be orthogonal vectors. And again, you can compute specifically from the solutions that you've obtained, the normalization factors. Then the Jacobi polynomials will be the overlaps. So you compute by a direct computation the overlaps of these vector Jn with Z tilde. You again get a 2f1 of 1 over Z. You use the FAP formula and you find the Jacobi polynomials. In Z, in the variable Z, which is on the unit circle, and a similar procedure again has two terms. You see one which will be a pure power series, no dependence on Z, and one which will be the Jacobi polynomials, but with these transcendental factors. The orthogonality follows again from the same completeness relation. We know that these two vectors are orthogonal, and so if you integrate over the unit circle, these functions of Z, they will be orthogonal. And after some substitution and simplification, you arrive at this integral I and N, which when integrated over the unit circle, you see with this weight, gives something which is an orthogonality relation. Now, this involves functions, whoops, pardon me, I apologize for that. This involves functions that are on the unit circle, and well, we would like to recover. This was a mistake, but I wanted to stress that this orthogonality is on the unit circle. And now you'd like to convert that to the interval 0, 1. This could easily be done using the following contour, where the integral over the big circle is found to be equal to the sum of the two integral below and above the branch cut. Observing the integral over the little circle is 0 if beta is smaller than 1. And then just performing that, you recover that this integral IMN is brought to the interval 0, 1, and it just coincides with the usual orthogonality relation for the Jacobi polynomials. All right, the last part, it goes like this. I want to use this framework to characterize the Askey polynomials. It's very easy to see that you don't lose any generality by taking the normalization constant to be 1, and then A tilde to be 0 and A equal 1. It ensures the relation that has to be there between the two. And taking the initial value, you see we were solving two terms occurrence relation, so there's always an initial value, to take this dn of 0 as this expression. And in so doing, it ensures that the overlap z tilde Pn is precisely the Askey polynomial. And then we can find the action of the operators L and XL in the basis Pn. These two operators are two diagonal in the basis Pn. So we start from the action or on the basis of the module, the defining representation, some Polynomial identities, which are quite simple, and you readily see, knowing the hypergeometric form of these vectors and using these properties of Polynomial symbol, you really readily see that L on Pn on these basis vectors gives Pn and Pn minus 1. But if you use alternatively this other identity, which is basically obvious, taking another factor in the hypergeometric expansion, you see that L on Pn is also affects shifts on the parameter, alpha plus 1, beta minus 1. In the same fashion, a little more involved, you find that R acts two diagonally also on these vectors Pn, this time increasing by 1 and with stabilizing term. We will also consider R tilde equal xm, but this is provided, the actions are immediately provided knowing that the action of m is just n times the action of L. Okay. So next, what is useful is to identify a differential model for the algebra. And this is easily obtained, recalling that the overlap of z with the basis tau k is just z minus 1 to the k. And so you infer, you obtain a differential expression by just finding the operator OZ that will just reproduce the matrix elements of O acting on tau k, then projected on z star. And in so doing, you readily see that with L given by this first order derivative term, M being the hypergeometric operator and X script just being multiplication by Z, you check that these realize the meta-Jacobi algebra. And then of course the product R and R tilde are just the corresponding R script expression that you obtain by using the corresponding operators for X and L. This model, you could also, this differential model can also be obtained from the Baruch-Girardello that's meaningful to you, the Baruch-Girardello realization of SU11. Okay, now we just computed or determined the action of L and R on the basis Pm. So if we project now over the basis Z, this will imply some differential identities. This is just a translation of these actions. And L is now a differential operator. If we act with this differential operator on P, it will give you this expression. And similarly with R, it will give you this raising relation. Okay, we have all the ingredients now to read off the bispectral properties of our Askey polynomials. So from the generalized eigenvalue problem, which we use so often, if it once projected over Z tilde, it becomes the second order differential equation, M, the hypergeometric operator, equals N times the action of L, which is first order on this polynomial. So you have a second order differential equation in the form of a GEVP. And for the recurrence relation, you now consider the generalized eigenvalue problem that R provides you with. Recall that R is made out of XL. So by construction, this X acts on Z, provides the Z, L is there. So this is the action of L script on the Askey polynomial. So you know that this generalized eigenvalue is satisfied by construction. And now if you use the two diagonal action of R and of L on these polynomials, we call these two diagonal actions, which are here, you just bring those in this relation, and this provides you the recurrence relation of R1 type, which is here. So it's R1 type, Z times the Pn terms with the coefficients given by these expressions. And the last piece of result is that the framework also gives you, very easily contiguity relation. We noted that L induces shift when acting on P by alpha going to alpha plus 1 beta to beta minus 1. The same goes for M because of the relation between M in the actions between M and L. And so projecting again with Z star gives you these two contiguity relation. In other words, acting with this first order operator on the Askey polynomials will have the effect of shifting alpha by plus 1, beta by minus 1. Very good. So let me briefly conclude. What have we obtained? Well, we offered a unified algebraic interpretation of both the biorthogonal Askey polynomials on the unit circle and the Jacobi polynomials on 0, 1. This picture was based on an algebra that we call the meta-Jacobi algebra, generated by three operators, L, M, and X. The Askey polynomials P, N, they arise as overlaps on the MJ module between basis for a generalized eigenvalue problem defined by L and M, and eigenbasis of X transpose. The biorthogonal partner Q are obtained from the reciprocal adjoint problems, from overlaps of the reciprocal adjoint problems. As for the Jacobi polynomials, they're obtained the same framework. In this case, we still working on the same module. We look at the eigenbasis or at the overlaps between the eigenbasis of M and those of X transpose, or vice versa. And we saw that the orthogonality relations followed very naturally. After that, having introduced a differential realization, we readily obtain the bispectral equation, the differential equation, as well as the recurrence relations for the Askey polynomial. And both were explicitly obtained and from the generalized eigenvalue problem. So my last remark is the following, that this algebraic description of the Askey and Jacobi polynomial is quite parallel to the one I was describing at the beginning of the talk, the description of the rational and polynomials functions of Hahn type. And we see there a pattern. In fact, we believe it should be possible to associate meta-algebras to most entries of the Askey scheme so as to simultaneously be able to describe the bispectrality of the hypergeometric polynomials and of the associated biorthogonal functions. With that, I would like to thank you very much for your attention. I'll be happy, hopefully, to answer questions in person. Thank you.